Okay, success. So, Kevin, are we ready? Okay, great. Okay, so generators, please start. Stefan, you start.
Trying screen sharing. It's okay?
Mm-hmm.
Okay. So, hello and welcome to Eurocrypt 2020. My name is Leila Batina and I'm your general chair together with Stjepan Picek. Stjepan?
Hi.
So we were supposed to host you in Zagreb around this time, but as you all know, it didn't work out. So we are running it as a virtual event. And although it's not so great as it could have been in Zagreb, of course, there are still some good things about having a Eurocrypt online. And one of those things is not like not having to wear pants, like tweeted by Cards Against Cryptography, but actually is having so many of you participating. So the 1K milestone we reached yesterday, like 17 hours ago, and there are still registrations coming in. So we have 50 plus countries participating. So it's really participants all around the world. And Stjepan will give you more on the Eurocrypt numbers.
Yeah. So welcome everyone to the first ever virtual edition for any IACR conference. As Leila already said, we are around 1,100 participants, 53 countries. What's very nice, there is around 300 new IACR members, and out of those, around 190 students. So this is the biggest ever IACR conference, which is the plus side of virtual event. More details on the statistics, because especially people are still registering, will be given tomorrow during the RAMP session talk. For sponsors, our diamond sponsor is Technology Innovation Institute. Our gold sponsors are Calibra, Visa Research, Google. Our silver sponsors, new slide. Our silver sponsors are Cloudflare, IBM Research, and our bronze sponsors, PQ Shield, Rambus, Platon, Hardware.io, SIA, Intrinsic ID, and Crypto Experts. Thank you all for your support. Leila?
Yes, sorry, it's still early in the conference, so getting used to everything. So this event has been brought to you by Kay and Kevin, and we really wanted to give a huge thanks to them, because they did a tremendous job after taking over from us after the physical event has been canceled. They just picked it up, and the result you will see in the coming days, and also you see today. So let's give them a round of applause. Yeah. Great. This works much better in the physical conference, but yeah, thanks for trying. We want also to thank our PC chairs, Anne Canto and Yuval Ishai, and of course the IACR president, Michel Abdallah, who were with us all the way from before and during the crisis. So we want to thank them for very smooth collaboration. And of course, the IACR Corona Committee people were constantly available in the past few months, and they were helping as well with this transition. So from the physical to this virtual event. And we will continue to update you on what's coming. You will hear now also a bit more from our program chairs and from Kay and Kevin themselves. But in the meanwhile, please follow us on Twitter. And if we are still allowed, I guess, to look forward to our hopefully next year physical event in Zagreb, which is now scheduled to run from May 2 to 6. And we definitely hope it happens, because otherwise Stjepan and me might end up doing general chairs for many years to come. So until we get it in Zagreb, we will stay on board. But the great thing is that many more people promised to stay on board that we're helping this year until we cancel. So Peter Schwabe is affiliated events chair. So he's your guy if you want to still organize it next year, but didn't make it this year. So we have a local team from Zagreb, Marin Golub and Domagoj Jakobovic, and our local communication team helping there as well, Simona and Shanley. So we hope to see you all next year in Zagreb. In the meantime, enjoy the conference. And if the coffee is not good, don't complain to us. Thanks.
Okay, so should I speak next here?
Yeah.
Okay, so I don't have any slides because we've made the website. So there's this old expression, RTFM, which you should be able to find all of your instructions on the Eurocrypt website. I'd like to introduce my daughter, Kay McKelly.
Hello.
So Kay and I have been putting together the website and trying to manage the technical operations of this. Some of you may not know who I am. I was actually president of IACR in an earlier era, much long ago. And my first Eurocrypt was in 1988. They were under different circumstances than this. We're moving to a virtual conference, and this is all a big experiment to see what works and what doesn't. The things that you should know is that you should read the code of conduct. You should enter with your real name into the list of participants, because that way the chat and the questions can be identified to a real person. And if you want to ask a question of the panel, then you should use the Q&A feature, which everybody should be able to see on their screen. You can send a question at any time. You don't need to wait for the end of a talk. People will be monitoring those to feed them to the appropriate people. There is a chat feature which you can also use. That's somewhat discoordinated, and so that the chat feature within Zoom, that is. And so we would recommend you try to use the Q&A whenever possible. Kay, did you have anything else to add to that?
No, other than to say welcome to the virtual conference. As a former sociologist who did internet research for a fair few years, this is especially exciting to me. I now work as a web developer and general go-to tech person for the IACR. So I'm very happy to be here and be a part of this.
And with no more delay, I turn it over to you, Val.
Actually, it's Anne who's talking first.
Anne, okay.
And we can't hear you, maybe.
Oh, you cannot hear me?
Now we can.
I had to unmute you.
Okay. Okay, so does it work?
Yeah.
Okay, so my name is Anne Contant. I'm one of the program chair of the conference. And as probably most of you, I have to say that I was very excited to spend 1 week in Zagreb. And I saw this maybe like a kind of a reward for the effort we spent handling 400 or almost 400 submissions. Well, but it seems I will have to do this a second time next year to earn my trip to Croatia. So as I said, we received a lot of submissions, 375 submissions, which is by far a new record. But this also means that this was quite a workload for the program committee. And so I would like to thank all PC members for their efforts. So I think you can see their names here. So they have all been very responsive, even when we had very strong discussions between Christmas and New Year. And again, they have been very responsive when we had to organize this virtual conference, and we were looking for moderators for the live sessions. So you cannot upload them, but they really deserve it. And I would also like to thank all speakers, because we ask them only like 3 weeks in advance to prepare pre-recorded video of their talks, and also to prepare a short presentation that we will have in these live sessions. And we received everything and all videos on time, which was quite unbelievable, I think, for us. And so thanks to all of them, because thanks to their responsiveness, then there's a pre-recorded version of all talks which is available, so you can watch it whenever you want. And this will be complemented, of course, by the shorter presentation and the discussion we will have during the live sessions. So last but not least, let me try to show you. We will have several special events during the conference. So first of all, we will have 2 great invited talks. Both of them will be live talks with queries and answers. So the first one will be on Wednesday, given by Alice Silverberg, and it will be on the relationship between mathematics and crypto. And the second one will be given by Alan Rosen. It will be on Thursday on fine-grained cryptography. And among all special events, we have, of course, the IACR membership meeting on Tuesday after the technical sessions. So you are all welcome to attend this meeting. On Wednesday, we have, of course, the RAMP session. So the submission deadline is Tuesday at 9 a.m. UTC time, and you will find all details on the website. But I would like to thank our 3 RAMP session chairs, Hilai Chen, Rishabh Goyal, and Lisa Cole, who accepted to do this under very unusual conditions. On Thursday, we have a very special event, which is a panel discussion on contact tracing. So we have heard very strong opinions on these topics recently, and we would like to restore some scientific discussion on the different aspects on contact tracing. And last but not least, on Friday, after the closing remarks, we will have an open feedback session where all of you are invited to provide any comments you may have on this virtual conference. So I think that's it for me, and I let Yuval add a few words.
Okay, so hi, can you hear me? Yes?
Yes.
Okay, good. So I'd like to thank my wonderful co-chair Anne, and join her in thanking the entire program committee, and also the general chairs, and Kevin and Kay, who all spent a huge amount of effort to make this virtual event happen. It's really a first of its kind, for us at least. And yeah, so I guess before moving to the technical program, let me make a personal plea, trying to appeal to the kind hearts of all you hackers out there. So yes, we realize that Zoom is not the most secure piece of software created by mankind. But yes, and this is why the IACR does not endorse Zoom. But if you engage in Zoom bombing or any other kind of malicious activity and ruin our party, then I'm afraid that the same IACR might declare my job as being incomplete, and I will have to serve as a Eurocrypt chair for a 3rd year. And then I will have a very hard time forgiving you. So, let me, I guess now is a good time to switch from this experimental form of security by begging to more principled forms of security, starting with number-theoretic cryptography. And I'm pleased to introduce the first session of the first ever virtual Eurocrypt. And the session moderators are Luca Defeo, Marc Joie, Cécile Pierrot, and Frederick Verkauteren. And without further ado, let the first session begin.
Okay, thank you, Yuval. So welcome to the first session of this online Eurocrypt, which is on number-theoretic cryptography. So the idea is that if you have any question for the speakers, you can post them on the Q&A. And we will assemble all the questions, and then during the discussion phase, which happens after all the talks were presented, we will answer, well, the speakers will answer your questions. So every talk will be a very short talk. It will be roughly 5 minutes. And the first talk of the session will be given by Chris Pikert, who wrote a paper on analyzing the security of CSAT. So Chris, the floor is yours.
Very good. Can you hear me?
Yeah.
Yeah.
All right. Thank you very much. And thank you to all the organizers for all their hard work in preparing this virtual event on such short notice. In this talk, I'll be telling you about using Kuperberg's collimation sieve, or C-sieve, or that is to cryptanalyze a recent post-quantum proposal called C-side. So given the short time, I'll start with the conclusions. The main conclusion from this work is that the proposed parameters for C-side offer us relatively little post-quantum security beyond what's given by the cost of quantumly evaluating the function itself on a uniform superposition. So for example, for the main parameters of interest that have been studied in the literature, C-side 512, we can do key recovery in only about 2 to the 16 or even fewer evaluations, quantum evaluations of the function using about 2 to the 40 bits, that is 128 gigabytes of classical RAM that is quantumly accessible. And I'll say a little bit more about what that means. So the main topic for the paper is the trade-off between evaluations and amount of RAM that's needed, quantumly accessible RAM that is. But we also give some estimates on the total quantum T-gate complexity for the entire attack. So for example, if we assume that the evaluation here costs not much more than for the best case distribution, which is slightly non-uniform, but very close to uniform, then C-side 512 can be broken with about 2 to the 60 T-gates and the same amount, 2 to the 40 bits of quantumly accessible RAM. And so the consequence is that it would fall well short of the claimed NIST level 1 post-quantum security. And as a reminder, NIST level 1 asks for security that's equivalent to AES 128 key search, which requires by NIST estimates about 2 to the 170 T-gates divided by maximum depth of your quantum circuit, where maximum depth is assumed to be plausibly between 2 to the 40 and 2 to the 96, looking out into the future. Other parameters of C-side were proposed, like C-side 1024. This is breakable with about 2 to the 72 T-gates and 2 to the 44 bits of quantumly accessible RAM. This means it also falls short of level 1. And a third parameterization, C-side 1792, which was proposed for NIST level 3, is also breakable with just a bit more T-gates and a bit more RAM. And therefore, it also does not reach level 1, possibly except for the very high end of the max depth range. So let me go back to the beginning with C-side. And this was a proposal from AsiaCrypt by Kostrick, Longa, Martindale, and Rennes in 2000. This is an isogeny-based post-quantum commutative group action, which basically means the following. We have an abelian group G and a set Z and some action star that acts upon, that takes an element of G and acts upon Z to return an element of Z. And this follows in the framework of Kovanes and Rostovtsev-Stolbanov. And in fact, everything we say will apply to this general commutative group action framework. I want to distinguish this from other isogeny-based crypto like SIDH, which does not involve abelian groups at all, and there's no group action. The big advantage of commutative group action is that it gives Diffie-Hellman style non-interactive key exchange. And in fact, the proposed C-side 512 is very efficient. We have 64-byte keys and very fast key exchange. And also recently there have been signatures that are very small in terms of public key and signature size. So the efficiency profile is very attractive, but what about the security? And the main problem for C-side or other commutative group actions is secret key recovery. So given public parameter Z and someone's public key A star Z, the goal is to find their secret key A or some equivalent, which is a group element. And it was observed by Childs, Zhao, and Sukharev in 2010 that this reduces to a hidden shift problem. And the hidden shift problem was actually studied in a quantum setting going back to the early 2000s, starting with Kuperberg. There are 3 main ingredients to a quantum algorithm for hidden shift problems. And we focus in this work on the sieve and measurement parts of these algorithms. As far as the sieve algorithms go, the original work of Kuperberg from 2003 required 2 to the order square root n oracle queries, where n is the log of the group size. There was an improvement by Regev, which actually increased the number of oracle queries, but reduced the amount of RAM quantum memory required. And then there was a third work, second work of Kuperberg, which brought the number of oracle queries back down to 2 to the root n, but also reduced the kind of memory that was needed, making it now classical, but only quantumly accessible. And that means it can be queried in a superposition over all the addresses of the RAM, but it's just ordinary classical memory otherwise. So Kuperberg's collimation sieve, or C-sieve as we call it, subsumes these prior 2 works and offers more trade-offs. For example, one can, if one makes the log of the number of queries and the log of the amount of RAM greater than about n, then the sieve is successful. So in our work, just to wrap up, we generalize and improve Kuperberg's C-sieve in a number of directions, and we analyze its concrete complexity on the proposed C-side parameters. This is a summary of the contributions. I want to mention that we run actual simulations up to the real C-side 512 group order, which had never been done before. And the simulations correspond very closely to the theoretical model that has been developed. So these are the previous works and the sieve algorithms that they were based upon. We get some substantial improvements by using the C-sieve instead, down to even about 2 to the 14 oracle queries with sufficient QRAM, and other trade-offs are possible. In the next talk, Bonatane and Schottenlohr also will describe some complementary and concurrent work that they did on the C-sieve, arriving at similar conclusions, but from a different parameter point in the parameter space. So that's the conclusion of my talk. These are the conclusions again. The paper is available on ePrint, and I'll encourage you to check out the code and the full talk. And that's all I have. Thank you.
Thank you, Chris. So again, if you have any questions, please post them to the Q&A. And then after the last talk of the session, there will be some discussion on all the previous talks in this session. So the next talk in this session is again on the quantum security of C-side and will be presented by Xavier Bonnetin. Can you share your screen, Xavier?
You're there. Can you share your screen?
Yeah, I no longer see my presentation in the things I can share, which is strange.
Look for the share screen. Oh, okay.
Yeah. It doesn't appear in Zoom, so.
In the meantime, maybe Chris can answer the questions so that we.
Yes, Chris, can you see the Q&A?
Yeah,
yes, I see
think
the
it should
question.
work now.
So the question is. Oh,
yeah, I guess.
Okay, I'll come to the question later.
Okay, let's go to Xavier then.
Okay, so now I will present another quantum security analysis of C-side. So as it was already presented by Chris, I will very quickly present C-side. So it's a crypto system whose hardness relies on the ability to invert an abelian group action. There have been 3 instances proposed in the original article that are expected to match the 3 security levels proposed by the NIST, levels 1, 3, and 5. And quantumly inverting an abelian group action reduces to what is called a hidden shift problem, which is presented here. So what we've done in our article is to put a focus on what we call hybrid attack, that is quantum attacks that differ part of their computations to a classical computer, with the idea that classical operations will be cheaper than we can add more of them. So for resources estimates, we consider that the limit we have is both for quantum cost, the quantum search on the corresponding AES crypto system, and classically a classical exhaustive search. For the quantum cost, we consider circuit models. We do not consider RAM access, contrary to what Chris did, because we don't really need that for many trade-offs, and we try to limit the amount of used qubits. And classically, we are less strict, and we allow RAM access and to be less precise. So the attack is in two parts. First of all, we need to implement the quantum oracle and then to solve the generic problem with hidden shift. And implementing this oracle is hard in general, but here, as we need to have an efficient protocol, we are given many isogenies of small degree, and we can leverage this fact to reduce the cost of the evaluation. This is done in two parts. First of all, we pre-compute the structure of the group with a Shor's algorithm. Then we get a good basis to evaluate any isogenies using these small degree isogenies that were given for free. And once we've done that, which is just a work that needs to be once for any seaside instance, for each quantum query, we will decompose the arbitrary isogeny we want to evaluate over this basis of cheap isogenies and evaluate the sequence. For our concrete estimates, we built upon the work of Bernstein, Lange, Martinez, Pani from last year's Eurocrypt with a quantum circuit very similar, but with two main differences. The first one is that we drastically reduce the amount of qubits we need from a few hundred millions to less than hundreds of thousands of qubits. And we use a different way to sample generators and elliptic curves using quantum sampling instead of alligators. This allows us to obtain some concrete cost estimates for these functions that we present here for the free instances of seaside. And of course, this is only one possible trade-off. And if we want to allow more qubits, it would require less T-gates. Now that we have our functions, we studied what we could do with the free possible hidden shift algorithm variants. So the first one is Kuiperberg's first algorithm. It's a sub-exponential algorithm, but it's very, very rigid. We can't make any trade-off between classical and quantum time, and it requires a large quantum memory. Nevertheless, we can still estimate what it can do. We've simulated it, and we've obtained this concrete complexity of the algorithm, which allows us to obtain the following table for the instances of seaside. We see that for large instances of seaside, then we have a lower amount of T-gates than what is expected. But the main constraint is that due to the fact that we really need to have a large quantum memory, the number of qubits quickly explodes with larger instances. And also, we are wasting a lot of classical time here. We can't really make use of this bound. If you want to do that, we need to go to look at some other quantum algorithms. So the first one is a Regges variant, which allows much more freedom in what we can do. So we have a customizable merging tree. We no longer have a constraint on the amount of quantum memory. We can stay always polynomial. And the main difference is that for each sequence in our merging tree, we will have to solve a random subset sum instance, and we can play on the size of this instance to increase the classical cost and having a smaller tree overall. And if you really want to go to the extreme and see what would happen with a tree as minimal as possible, then we obtain what is presented here. So an attack that would require a very limited amount of query, only quadratic in 18 square queries. But classically, we would need to solve large dimensions subsystem instances with the best exponent at the time in 0.291 and time and classical memory. And this allows us to obtain some other cost estimates for the free instances of seaside that are presented here. As expected, the number of T-gates is much lower, and so is the number of qubits required, but the classical time is much higher and quickly explodes as it is exponential. But if we allow for a higher quantum cost, it will also make us reduce the classical time. So this is one possible trade-off with Regges variant, but there is also another way to do it with Kuiperberg's second algorithm, which is in general more efficient, but however is more constraining on the array and the possible trade-offs you can do. In particular, if you want to have a very low amount of quantum queries and classical memory, you can do much with this new algorithm. But for if we can apply it, it's more efficient. The main difference is that instead of reducing to subset sum, it reduces to solving k-list instances, and we have still a lot of freedom. And for example, we proposed an instance with 4 lists merging, which gives this new cost estimates for this algorithm. We see that the number of tickets is higher than before, but not that high. We still have a very low number of required qubits, and the classical time that we need, it's much more reasonable on scale, much more smoothly than with the previous approach. And of course, this is only one possible trade-off. There are many more that we can think of depending on the amount of resources we have. So we can think of what would be some safe instances. And unfortunately, the metric we use and security levels we consider aren't really precise enough to give a strong fixed answer. So here we propose 2 distinct set of parameters that would be large enough for our attacks to cost too much. So the first, and they depend on essentially what is the maximal amount of classical memory we allow, and what are the assumptions we make on the quantum oracle for the number of queries we'll be able to do in the algorithm. So if we want to be aggressive, we suggest a prime of roughly 2,000 bits. And if we want to be more conservative, then it will be closer to the 5,000 bits. Now, to conclude, we studied many hybrid attacks on C-side that have many degrees of freedom and allows for a lot of trade-offs. As all these algorithms are sub-exponential, this means that estimating safe instances is harder than when we have exponential algorithms. And finally, we should recall that as we consider concrete time for these attacks, if we have an algorithmic improvement of the classical evaluation of C-side, this may lead to the same algorithmic improvement for the quantum circuit, hence improving the attacks. Thank you for your attention.
Thank you, Xavier. Now I will call the next talk to share its screen. It will be double base chains for scalar multiplications on analytic curves by Wei Yu, Saudal Musa, and Baoli, and Wei Yu will be the presenter.
Hello, everyone. I'm Yu Wei. My topic today is double base chains for scalar multiplications on elliptical curves. A double base chain represents an integer as the sum of 2 integers. We present 3 results of double base chains. First, we display a structure of the set containing all double base chains and propose an iterative algorithm to compute the number of double base chains. This is the first polynomial time algorithm to compute the number of double base chains. Secondly, we present an asymptotic lower bound on the average Hamming weights. This answers an open question for more than 10 years. Thirdly, we propose a new algorithm to generate an optimal double base chain. This algorithm accelerates the recoding procedure by more than 6 times compared to the state of the art work. We first discuss the number of double base chains. Counting the exact number of double base chains is useful to show double base chain is redundant and to generate an optimal double base chain. Imbert and Philip proposed an algorithm to compute the number of unsigned double base chains. Later, Dash in 2014 proposed an algorithm to compute the number of signed double base chains, but his algorithm is exponential time. we show the first structure of the set containing all double base chains. Based on this structure, we show an iterative algorithm to compute the number of double base chains. This is the first polynomial time algorithm to compute the number of double base chains. For the Hamming weights of double base chains, Dutch and Habig in 2008 posed an open question to decide whether the Hamming weights of double base chains produced by the greedy approach is sublinear or not. This question has been remained unsolved for more than 10 years. There are some efforts to investigate the lower bounds of double base chains, but these results are not enough to solve the lower bound of the Hamming weights of the double base chains. We show that an asymptotic lower bound of the average Hamming weights of double base chains for logarithm n bit integers is logarithm n over 8.25. This result answers Dash's open question. Now we focus on producing optimal double base chains. Dash in 2014 presented the first algorithm to produce an optimal double base chain, as Dash's algorithm is exponential time. In 2015, Carbonet and Elliott proposed the first polynomial time to compute an optimal double base chain. In 2017, Bernstein, Trentin-Soup, and Lang proposed a DAG algorithm to compute an optimal double base chain. Their algorithm was the state of the art. We proposed a dynamic programming to compute the number of double base chains. Our algorithm is over 6 times faster than Bernstein, Trentin-Soup, and Lang's algorithm. Experimental results show that scalar multiplication using our optimal double base chain is about 30% faster than that using non-adjacent form on Weierstrass curve. Now I briefly conclude this work. We were concerned with the theoretical aspects of double base chains arising from that study to speed up scalar multiplication and producing an optimal double base chain efficiently. Thanks for your attention. This is all I wanted to share. Please feel free to ask any questions.
Thank you very much, Wei Yu. Now we prepare for the next talk. Please post your questions to the Q&A that will be asked after the last talk. The next talk is going to be Rational Isogenies from Irrational Endomorphisms by Wouter Kastrick, Lawrence Panny, and our beloved panelist, Frederick Vercauteren. And Wouter is going to present the paper.
Okay, so thanks to the organizers for making this possible. So yeah, as I said, this is joint work with Lawrence Panny and Frederick Vercauteren, and our whole paper revolves around the diagram that I'm about to draw here. So if we want to break C-side, we are looking for a secret ideal class that takes us from this starting curve E0 to a given curve, say Alice's public key E. Okay, and now it's a general fact that this same secret ideal class takes the quadratic twist of this curve back to the starting curve E0. Okay, so we have this diagram. And what is the quadratic twist? Well, it's a curve which is isomorphic to this curve E, but not over FP. You have to go to a quadratic extension of FP to see the isomorphism. And for instance, this is an instance of such an isomorphism. And you see this I here, which as usual denotes the square root of -1. And since P 1 went to 3 mod 4, this indeed leaves over an extension. Now, on the other hand, there should also exist an ideal class taking e to et. And actually, if you look at this diagram, it's easy to tell what it has to be. It has to be your secret ideal class to the power -2. Why is that? Well, because going around the circle should amount to the same thing as applying the trivial ideal class, because that's the only ideal class that takes E0 to itself. Okay. And so in this paper, we concentrate on this composition here. Okay, so we have this map here corresponding to this ideal class, and then we have this non-rational isomorphism back. And so together, this gives us a map from E to itself, so an endomorphism of E. And because of this non-rational component, it's actually an irrational endomorphism. And so our whole paper studies to what extent this reasoning can be reversed. So if we are given irrational endomorphisms, one or a few, can we somehow force them into this framework and then extract from this information about this ideal class? And then once we have this ideal class, it's an easy fact, or it's an easy task to derive the secret ideal class A from that. Okay, so that's the setup. And so here are our conclusions. So first of all, well, this is not a deep statement, but this characterizes the non-rational endomorphisms that fit inside that framework. So those are exactly the endomorphisms that are anti-commuting with Frobenius. So applying Frobenius on the right or on the left gives a difference of a factor -1. We call such endomorphisms twisting. And then we deduce the following reduction. So starting from an endomorphism which is non-rational, so not defined over FP, then we can easily convert it into a twisting endomorphism, and then this allows us to play the previous game, and then it's easy-ish. There's a small subtlety here, but I will skip it to obtain the secret ideal class A from this. And then there's something that I didn't mention on the previous slide, but finding the ideal class A does not really break C-side yet. You still have to replace this representing ideal with a equivalent ideal, which is very smooth. And that's a classical step, but unfortunately, that's not a polynomial time step. So this involves class group computations and then lattice reduction. Okay, but we also argue in our paper that it's somehow intrinsic. So it's not to be expected that you can avoid such a step when playing the game that we want to play. Okay, so more details in the paper or in Loren's longer video. So the conclusion here of this first contribution is that if you have sufficient knowledge of the endomorphism ring, then basically the security of C-side reduces to the hardness of this third step, say, and that's much easier than anticipated. So it drastically weakens the security of C-side. And we view this as the C-side version of similar conclusions that have been drawn in the context of SIDH, mainly by Galbraith, Petit, Shani, and T in 2016, sorry. And then a second contribution addresses the open problem of hashing into the isogeny graph. So concretely, we want to find a method for producing a supersingular elliptic curve over FP, which does not come with a known path to our base curve E0. Okay, so that's an open problem. And for the moment, we have two methods for constructing supersingular elliptic curves over FP. One is by reducing well-known curves over Q, modulo P. So this is following a strategy outlined by Breuker in 2009. And then a second one is more trivial, is starting from such a supersingular curve, you apply isogeny walks. But the second method is clearly not useful for hashing, because the person doing the walk knows the walk. So what about the first method? Can we use CM constructions for hashing into the C-side graph? And so our answer is very negative, actually. So we prove a precise theorem, but I only state an informal version here, saying that these reduced CM curves, they naturally come with such a twisting endomorphism from before. And so this allows us to play the previous game, and this will reveal the precise location of these curves in the C-side graph. And so the bottom line is that they cannot be used for secure hashing into the C-side graph. So I'll stop here.
Thank you very much, Wouter. So this was the last talk on C-side, I promise. The next talk is going to be low-weight discrete logarithms and subset sum in 2 power 0.65 n with polynomial memory by Andre Esser and Alexander Mai. And Andre Esser will present the paper.
So can you hear me?
Yes.
Nice. Thank you for the introduction. So I'm Andre, one of the authors of the paper. So in the paper, we actually studied algorithms for solving both problems mentioned in the title. And we had a focus on memory complexity. And yeah, most of our algorithms possess only a polynomial amount of memory. And first, we were able to abstract both problems to a more general problem, which we call group subset sum. And we were also able to generalize algorithms, which were mostly known for the subset sum problem to this group subset sum problem. And so we could also apply them to the low weight discrete logarithm problem, which in the case of the DLP directly improves on previously known approaches. So also we gave improved algorithms for both problems, which had mostly two key ingredients. So we try to carefully define functions where collisions between those functions actually relate to our solution, or at least some of the collisions between those functions. And then we use standard techniques for collision search to find collisions in a memoryless fashion. And for our functions, actually x plus y for a colliding value is sometimes equal to the solution. And then we exploit the fact that such a solution z can be represented as a sum of many different x and y. And obviously, the domain of the functions plays a major role in how many representations there exist. So we try to optimize the domains of our functions to maximize this amount of representations, and hence have a better chance to find one of these collisions. So in the low weight DLP case, we actually heavily exploit the fact that this summation x plus y is computed over the natural numbers. So usually in the subset sum case, where this technique comes from, x, y, and z are vectors, and you're performing a vector addition. So addition is performed component-wise. But if you're performing an addition over the natural numbers, there are carry bits, and that is what we exploit to increase the amount of representations. So this enables us to give improved algorithms in the polynomial memory setting. So the time complexity is improved in comparison to other algorithms. And also we can give a time memory trade-off, which meets the lower bound for generic algorithms for the problem, but give, in comparison to the meet in the middle algorithm, a reduced memory complexity. So in other words, we reduce the memory complexity of the meet in the middle algorithm. So in the subset sum case, we introduce a layered collision search where the function definitions themselves or the functions are defined over a collision search. So each evaluation of the function itself performs a collision search. And then we perform a collision search of this between this outer function, so a collision search over collision searches, which has the benefit of that we represent our solution as the sum of 4 addends instead of just 2, which drastically increases the amount of representations, which enables us to give an algorithm with time complexity 2 to the 0.65n and only a polynomial memory requirement. Thank you very much.
So thank you, Andre, for your talk. So the idea now is to have a 25-minute or a bit less than 25-minute discussion on the different papers. And there are already a bunch of questions in the Q&A, and we will go through the questions in the order of the papers. So let's first start with the first 2 talks on Seaside. And I guess the main question that people are asking is, how much larger do the parameters have to be now in order for Seaside to qualify for NIST level 1? So this is a question both for Chris as well as for Xavier.
Well, we proposed 2 sets depending on some interpretation. I know that it is not necessarily that satisfactory, but I think the most conservative of the 2 should be enough if you're concerned.
What's your opinion, Chris?
So in my work, I didn't give new parameters, trying to hit level 1. Although it looks like Seaside 1792 doesn't reach level 1 under the assumption that you can implement the Oracle in about the amount of T-gate complexity then that matches the best case distribution. So it looks like it would be prudent to go, comfortably above 1792 at the minimum.
Mm-hmm. Can you highlight the difference between the two papers? So between your paper, Chris, and between Xavier's paper?
So we don't really consider the same model because we focus on hybrid attack, and we propose concrete cost, that is a total number of gates that we estimate, and we've studied more algorithms and trade-offs thanks to that, right? And also we don't use quantum RAM. Well, quantum accessible classical RAM. I think that's it. I don't know if you want to add something.
Yeah, right. My paper focuses entirely on the collimation sieve with moderate amounts of, or even high amounts of quantumly accessible RAM and low arity. So I only look mainly at binary arity on the collimation sieve. And I also give software that lets you actually simulate the algorithm completely, so you can run it at the size of the full Seaside 512 group order, and it confirms that the theoretical model matches the the real world performance, at least in terms of the classical part of the sieve.
Mm-hmm. So in Xavier's paper, there is really a number of qubits given. I think it's around 40,000, which is for the oracle call. So in your paper, Chris, do you need anything else qubit wise, or is all the rest is just quantum accessible memory?
I think I missed the question. It got a bit garbled, but I think the question was the qubit complexity. Is that right?
Yeah, exactly.
Right. So I just take the existing estimates for implementing the oracle. I don't do anything concerning that. And then given those estimates, I plug that into the broader framework of the sieve to get overall complexity estimates. So whatever the oracle costs, the number of evaluations, 2 to the 16, 2 to the 14, whatever, you're going to have that query cost times the oracle cost.
Mm-hmm. So Leo also asks a question on the Q&A to Xavier. He says, if one uses lattice algorithms for the subset sum, you can get exponentially many solutions, almost as short as the shortest one for no added cost. Can you also use this within Regis algorithm?
Unfortunately, I don't think so, because we really need to have only, I think the short means that we have a small weight, and we really need to have only zeros and 1 here. So I don't think that could help. We may try to make things work with some other variants, but if you have a hidden shift with more than 2 shifts, but here this is not the case, and yeah, I don't think we can gain thanks to that.
Mm-hmm. There's a fairly general question here that says, is Seaside broken or done? So again, to both of you.
I'd say the parameters that were proposed are too short, but done, I think it's a strong statement. It's still pretty unique with a commutative group action. So yeah, I don't think it loses all its interest just because the parameters are larger.
Okay, Chris, do you want to add something, or?
Sure. Yeah. I mean, I don't think you could say anything's done. It does seem that we need to increase the parameters quite a bit. I think the only, someone can correct me if I'm wrong, but the only real implementation that I've seen was for Seaside 512. So I'd be curious to see, we can estimate how big the keys and signatures would be for substantially larger Seaside parameters, but I'm not sure about the running time cost. I think Seaside 512 was about 80 milliseconds. Maybe that's been improved somewhat for key exchange. If we go to 2000-bit prime or more, what does the performance look like? Because one of the most attractive features of Seaside was the high efficiency in space and time. But how does that change if the parameters have to get much bigger?
I think I can add an element of response to this question, because there is a paper that is not in the program of Eurocrypt that just appeared on ePrint a month ago, where together with Dan Bernstein, Benjamin Smith, and Antonin Leroux, we implemented a decently optimized version of Seaside 1024, which now runs like the 80 milliseconds figure is more for Seaside 1024. So I expect more work to be done in the next months on this kind of algorithms for higher security level in Seaside. So it shouldn't be completely undoable, but of course we are going to lose in performance.
So the next question is again for Xavier. So Chloe asks, in your parameter suggestions, have you taken into account Chris's sieve?
As the parameters and the models we consider are a bit different, technically no, but I think it would still encompass Chris's algorithm, but I have not explicitly checked that it is the case. So.
And is there a combination of the two papers that will lead to even worse parameters?
I don't know. More precise, I guess, because with more simulations of Kuiperberg second algorithm, we can get more concrete estimates for a wider range of available resources. Worse, I don't know. The asymptotics don't change
It would be,
that much.
Yeah, it would be straightforward to plug in the other recommended parameters to the model in our paper to get an idea of how many Oracle queries and how much RAM would suffice to break these other larger parameters. That would give you an upper bound on the hardness of the problem. Of course, I think there probably are reasonable and useful points in the parameter spectrum between our two papers. For example, to consider somewhat larger arities in the collimation sieve, so not just binary trees, but 4-ary or 16-ary or something like this, using larger amounts of QRACM. I didn't use very large numbers in my paper, so I think there's more to be done in the intermediate between what the two papers did.
So I would like to add that the trade-offs I presented in the presentation corresponds to a 4-ary a tree with arity 4, but we're less precise in the analysis than with Chris's paper and the binary trees.
Okay, thank you both. So we will now move on to the next paper, and Mark Shaw will take over.
We have a question on the one of Kashayar is still for Xavier, I think so. Yes. So, so he says, if I understand correctly, if implementing the oracle relies on the rapid mixing property of the ideal classes and is pretty heavy itself. The problem is if we consider curves of larger genius, we won't have the mixing property. I was just curious if there is any other approach to compute the action. Is this for Xavier, I guess? No?
So I don't really know, quite frankly, but what I can say is that as long as you have an abelian group action, you can use a quantum hidden shift algorithm. And if you can manage, whatever the way, to make an efficient or somewhat efficient crypto system classically, you should be able to use similar techniques to make a quantum record that would not cost that much. But I don't know the details for higher genius curves.
There was also the question of Dan Shepard. He asked, do any of the variants associated with C-surf design affect any of these analyses substantially. I think the answer is almost everything, if not everything in these papers would apply equally well to CSURF. It falls within this commutative group action framework, and CSURF is a small tweak of CSIDE. So I would expect the Oracle complexity estimates to be very similar as well.
I agree. We don't attack the key exchange, we attack the group action.
Okay, so let's move on. So for the next paper, so there was just one question, and the question is, so that's for UA. Could you elaborate on what is meant by optimal for DBC?
Yeah. One question is that you have defined optimal by minimal costs. Given the sets of all double best chains of a positive integer n, which might contain infinite number of elements, if I got it right. Can you say something about the existence of a minimum? This is a good question. That's right. The DBC of a positive integer n is always infinite, and the existence is obviously. For example, binary representation is a special case of double best chains, and there is a cost when we perform scalar multiplication. Then this cost is always positive, and as our algorithm can compute the minimum cost, and this cost is always existing.
Okay, so I just want one more short question for you. Is your recording algorithm protected against side channel attacks? And if not, what do you think will be the cost to make it protected against side channel attacks?
Latex?
Just the recording. So
the recording is about 6 times than the previous best algorithm, but this time isn't can't be ignored compared to the time of scalar multiplication.
Yeah, so the question is it protected against side channel attack, the recording? Is it secure against, let's say, timing attacks, for example? Is it time constant?
Side channel attack?
Yes.
The recording procedure.
Okay, thank you.
Yeah, we can use side channel atomicity to prevent the side channel attack in my scalar multiplication to perform scalar multiplication using double best chains.
Okay, but I was thinking about the recording, not the scalar multiplication.
Sorry, I didn't think this. The recording procedure can't prevent a side channel attack. Yeah.
Okay, thank you.
Thank you.
Thank you. Now we move on to the next talk. So we have a couple of questions for Wouter, who's been already answering them in the Q&A. So maybe you have a longer version of the answers, but I would like to invite Wouter to repeat his answers to everyone who's listening. So the first 2 questions are kind of related, is about what you can do with quantum computers. So there's one by Alexei Vodovenko, who asks whether it is easier to do the smoothing step using a quantum computer. And one of which I think it's related, so I'll ask it right away, is by myself. And I was curious, in your YouTube video, you had you mentioned a reduction between the discrete logarithm in the class group and the algorithm to convert between ideal and isogeny. I wonder if this has any impact, any application for quantum reduction problems.
So yeah, for your second question, this this reduction is indeed void in the quantum setting. So it's used as an argument that we probably cannot avoid this step 3, but it's a classical reasoning. So that's true. Yeah, in the quantum setting, we don't have such an argument. Yeah, because computing discrete logs in the quantum setting is easy anyway. So the reduction is pointless there. As for the first question, so if this question is about this smoothing of ideals, if that's easier given a quantum computer. So this amounts to 2 things basically. First is you have to understand the class group structure. So in terms of your generators, you want to find the lattice of relations, and that step is indeed much easier using quantum computers. So that can be done in polynomial time. But then for a given ideal, if you want to smoothen it, say, that amounts then to a closest vector problem in that lattice, and that's that their quantum computers are less of a help.
Okay. The next question is about the twisting endomorphism, the condition on being a twisting endomorphism. Barinder Singh Banvait is asking whether this is a strong condition or not, how easy it is to find a twisting endomorphism.
Yeah, I was just typing an answer to that question, so let me finish that later. But so it's an easy problem. It's basically linear algebra in dimension 4. So if we think of the endomorphism ring as like living inside this quaternion algebra generated by 1, I, j, and ij, so those are our 4 basis elements. Then in our notation, j corresponds to Frobenius, so the space spanned by I1 and j is completely known. That's a 2-dimensional space that's completely understood. And as soon as you have something which is not in there, you have a 3-dimensional space at least that you understand. And you are interested, so the twisting endomorphisms, they form a 2-dimensional space. That's the space spanned by I and I times j. So basically it's intersecting a 3-dimensional space with a 2-dimensional space, and that's linear algebra. So you will, it's easy to find. Yeah.
Thank you. And then we have one last question, which is, do you have any concrete example for contribution 1? So I'd ask you to recall what contribution 1 is, and then the example, I think you wrote it in the Q&A.
Did I? No. Somebody else replied to this question in the Q&A. So no, do I have a concrete? So contribution 1 was a reduction from knowledge of irrational endomorphisms to constructing this this secret ideal class A. Maybe I had a slide that I didn't show. Maybe I can go to that slide. It's actually that slide. The goal was to illustrate contribution 2, but I think it also illustrates contribution 1. For instance, imagine you are trying to locate this curve, y squared equals x cubed plus 1. Well, from this curve, we know that there is an irrational endomorphism, which basically corresponds to it's of degree 3. It's like, yeah, maybe it's a bit tricky to try this live, but basically, if you multiply x by a third root of unity, you get an automorphism. And if you do 2 times this automorphism plus the identity, then you have an endomorphism of degree 3. And then basically, if you play the game that we did in contribution 1, this will be the ideal that you find corresponding to this twisting endomorphism. So that will be the outcome. It's a bit cheap, my example, because it's already of a very small norm. So this does not really illustrate. Well, okay, let me maybe do this also. So this was the equation you had to solve. And so we know that this is our secret ideal class to the power -2, but we also know in this example that it's this. And so yeah, now we have to compute this a negative square root, say, of this. And so here we use, okay, maybe it's not all very convincing as an answer, but here we use the class group computation that was done in the context of CSIDE 512 by Burens, Kleinjung, and Vercauteren. So there we fully know the lattice of relations, and the dimensions of that lattice are small enough to allow for an easy solution to the closest vector problem. And so if we feed that to this to these algorithms, then this spits out a short a vector of short exponents. So this corresponds to a very smooth representative of the same ideal class. Okay, so that's, I guess, the best answer I can give live, but let me maybe think of another example in the chat.
Thank you. Now we can switch to a question to André Essa, which is maybe the last question of this session. So André, the question is, well, you have two questions. The first one is memory complexity important for solving information set decoding? And can your method be generalized to such decoding problems?
So yeah, I would say it's highly depends on the instances considered, but in general, I would say yes, memory complexity is important for solving information set decoding and LWE. But so especially if in considering polynomial memory algorithms, if you consider like very efficient implementations and optimized implementations. So having for both problems faster algorithms that only use polynomial memory is, I guess, highly desirable. But so for information set decoding, for example, having an algorithm with polynomial memory requirements that is faster than Prange's algorithm would be a big deal, I guess. But we tried to translate our algorithm to the information set decoding setting, where it unfortunately did so far not really give an improvement. So it's a negligible improvement on the 6 or 7 decimal digit. So yes, we tried to generalize, but it did not work out so far.
Okay, thank you. So I guess we have finished with the session. Maybe we can upload all the speaker, and if you cannot upload, you can raise your hand. You have been more than 400 to see us, so thanks a lot. And we have a 15 minutes break, I think. Thank you.
Okay. So everybody, please rejoin the next session, which is this paper session.
I'd like to point out that the link for joining the next session will be different than this link. You have to go to the program.
Very important, yes. Okay, thanks everybody.